As we continue to work through modeling functions, this video will cover the information on the back side of your graph. I apologize because the graphs that I chose are very faint, so one of them you can't see, so you'll have to kind of draw in when we talk about discrete versus continuous data. If you recall from the first video, I mentioned when we join points, that is when we have continuous data. So we think about the types of graphs we're going to have. When we're just inputting in a function rule, those kinds of graphs will always be continuous. Then, we also are going to talk about real-world problem solving, real-life examples. So if you think about example 2 on page 264, follow along as I read. Suppose your group recorded a CD. Now you want to copy and sell it. One company charges $250 for making a master CD and designing the art for the cover. There is also a cost of $3 to burn each CD. The total cost, or the function, is the P of C. It depends on the number of CDs burned. So the price is the function P of C equals 250 plus 3 CD. Notice they made a table. They inputted values, and then they graphed them. When they graphed them, they connected the points. Think about what that might mean. Skip down to example 3 for a moment. It's talking about photography. An automatic photo booth charges $3 for a sheet of photos. The function C of P, or the cost of the photos, so C of P equals 3P. It describes the cost of however many sheets of photos. Notice that graph has a table, data inputted, and then the data is not connected. What is the difference between the data being connected and the data not being connected? Money, or what you're going to be charged, versus number of photos or sheets that you're going to get out of the booth. One of the graphs, we can have fractions and decimals. The other one involves a count of items, meaning we have to have whole numbers. Continuous data involves fractions and decimals. They have meanings. When you're talking about money, when you're talking about weight, you're talking about things that could have a fraction of something. You can have part of $1. What do you think the graph will look like where we have continuous data? Well, example 2's graph is a line. That leaves data that involves a count of items as discrete. And when we have data that involves just a count of items as discrete data, like example 3, you cannot buy part of a sheet at the photo booth. That means we cannot connect our dots. So the graph is just going to be points. If you look at the 2 examples that I have here, the first example, is that discrete data or continuous? You are correct, Brandon. It is discrete. I've only plotted the points. The numbers in between the points do not have a value. They do not satisfy my real-life situation. That leaves this one over here with the graph, with the line, I know it's very faint on yours, as continuous. The part of the graph in between the points has meaning. I want you to look at example or quick check number 3 on page 265. It says determine the function rule models discrete or continuous data. We're not going to make a table and graph. We're just going to talk about this quick check. A, your family is hiking uphill from a campsite 4,000 feet above sea level. You climb an average of 500 vertical feet each hour. This function, h equals 4,000 plus 500t, relates time to your height above sea level. Do you think this is discrete or continuous data? Then look at B. The function C equals 6 and 50 hundredths t, or $6.50 t, represents the cost of T tickets to a baseball game. Is that graph going to look like discrete or continuous? Take a moment and decide. What did you come up with for A? Continuous. Correct. What did you come up with for B? Discrete. When we think about this, you might be saying, why is B discrete? Because my cost could be a fraction. You're right, your cost could be. But could we buy part of a ticket? We cannot. So when you talk about continuous and discrete, you need to make sure that both parts of your data can be part involving fractions and decimals, where they have meaning for both sides. Let's look at graphing special functions. My graph kind of got messed up here. This is supposed to be, let me write this in, f of x equals the absolute value of x minus 1, and this one is f of x equals x squared plus 2. While these are going to be special functions, we're not going to treat them any differently than what we did in video 1. If you look at your 3 steps. Step 1 was to create a table. So let's do that. We have x, and we have f of x. And remember I said we need at least 3 values or 4 values. I'm going to do 4. I'm going to do 2 negatives and 2 positives. I'm going to do negative 3, negative 1, 1, and 3. So to find f of x, I'm substituting that in. The absolute value of negative 3 is 3, and 3 minus 1 is 2. The absolute value of negative 1 minus 1 is 0. The absolute value of 1 is 1, and 1 minus 1 is 0. The absolute value of 3 is 3, and 3 minus 1 is 2. Now we're going to graph these 4 points. Negative 3, 2. Negative 1, 0. 1, 0. 3, 2. You're thinking to yourself, this might look like a funny looking graph. It's going to be slightly different. You might want to put in an extra point 0 so you can find where it crosses the y-axis. And the absolute value of 0 is 0 minus 1 is -1. 0, -1. What shape does this begin to look like? It begins to look like a V, and it is going to have a V shape. That's why the poster on my wall, my new poster, when you look at functions of graphs, function graphs, these are the special ones. Notice this is an absolute value. Absolute value graphs look like a V. Now we're going to come over here and we're going to do the function of x squared plus 2. So I'm going to start with my x value and get my f of x. Maybe it would be good for these if we do 5 points, 2 negatives, 0, and a positive. And I'm going to just do -2, -1, 0, 1, and 2. So I'm going to plug these in. -2 squared, that's 4. 4 plus 2 is 6. -1 squared is 1. 1 plus 2 is 3. 0 squared is 0. 0 plus 2 is 2. 1 squared is 1. 1 plus 2 is 3. 2 squared is 4. 4 plus 2 is 6. So we're going to plot -2, 6, -2, 6, -1, 3, 0, 2, 1, 3, and 2, 6. It looks similar to this one, but not quite the same. This one is going to take more of a U shape as you stretch it out. Because when we talk about squared functions, take more of a parabola shape. We will do more investigating with those a little bit later. I would like for you to try and graph for tomorrow, or for today, excuse me, number 16 and number 20 on page 266.